It was actually my pleasure to mentor Isabelle this summer. Isabelle is a rising high school senior in the San Francisco Bay Area. One of the things about Isabelle is that being neurodiverse herself, she understands firsthand the importance of accenting your strengths rather than focusing on your challenges. And I have to say that Isabelle brought some wonderful strengths to our project. I mean, we made great progress because of what she brought to the table. In addition to being definitely a STEM student, she has also a love of music. She's the varsity drum major in her high school's marching band. She holds a licentiate of the Royal School of Music in piano performance, and she's been tutoring piano students who are on the spectrum for the past 2 years. So she's an amazing person. We've done wonderful work. Isabelle, tell everyone about it.
Right, so I'm going to share my screen for Isabelle. There we go. Take it away.
Thank you, Deborah, so much for the introduction. Next slide, please. Because we have 2 projects, I will first give some background information about our projects and then talk about them individually. Next slide, please. First, some background information. Micrometeorite bombardment and solar wind are the 2 main processes objects in space are exposed to that change the spectral properties of the surface they interact with. Next slide, please. Micrometeorite bombardment occurs when tiny dust particles, or tiny meteorites, move really fast and hit the surface of the moon and the asteroids. This also alters the minerals by melting the top layers, forming little impact craters, reducing the material on top, and forming iron particles that are somewhat larger than those made by solar wind ions. And therefore, we call them big iron particles. Next slide, please. Solar wind from the sun contains ions, i.e. electrons and protons, that disrupt the iron-oxygen bond, releasing the oxygen and leaving the iron as little pieces of debris called nanoscale iron. This process produces the smaller pieces of iron called little iron particles. The change in the structure of the minerals can be seen in the spectra, where the presence of little iron particles causes reddening of the light reflected. Next slide, please. As we mentioned, the 2 main types of space weathering, micrometeorite bombardment and solar wind, change the spectral properties of the surface they interact with. They both do so by making the spectrum darker and the absorption band shallower. For the moon, both processes will make the slope steeper, which makes it look redder, because reflectance increases more dramatically with increasing wavelengths. For asteroids, it depends on how dark or bright the asteroids are. If it's a brighter asteroid, the slope will be steeper and it will appear to be redder. If it is a darker asteroid, the slope will become flatter and basically it will appear bluer. Basically, how the slope is changed by the processes depends on the surface composition. We understand these processes for the moon, but not so much for the asteroids. For materials on the moon, the change in slope depends on the size of the iron particles. That is, little iron particles make the slope redder, but big iron particles don't change the slope. On asteroids, we don't yet understand what causes On asteroids, we don't yet understand what causes the different slope changes. We see them in experiments, but we are still working to understand them. Nevertheless, we know that it takes micrometeorite bombardment much longer to do the same amount of weathering as solar wind, and that the younger the surface, the more important the space weathering by solar wind radiation becomes. Next slide, please. Here is our first project, micrometeorite bombardment on asteroids. Next slide, please. So for project 1, just some context first. Carbonaceous chondrite meteorites might be coming from C-type or carbon-type asteroids. However, the spectral properties of the asteroids and the meteorites are different. and we think it is most likely because asteroid surfaces have been space weathered, but the meteorite surfaces did not go through space weathering. In our first project, the goal is to understand how space weathering from micrometeorite bombardment affects a common mineral found on very dark asteroids. This type of mineral we are studying is a clay mineral called serpentine. We are trying to understand the spectral properties in this clay mineral due to micrometeorite bombardment. We know how the minerals on the moon are affected by the space weathering, but we are yet to know how clay minerals on C-type asteroids are affected. So that's what we want to find out. More specifically, we don't really know the role of micrometeorite bombardment in weathering the clay material on the asteroids. We are especially interested in the difference that micrometeorite bombardment makes. Does micrometeorite bombardment produce changes in the spectra that could explain the difference in the spectra between C-type asteroids and carbonation chondrite meteorites? So our research question is, does micrometeorite bombardment affect the spectra of asteroid surfaces so that they don't match the spectra of meteorite surfaces? Next slide, please. In an experiment done at the Vertical Gun Facility in the Experimental Impact Laboratory of the Johnson Space Center in Houston, Texas, they took a mineral commonly found in carbonaceous chondrite meteorites, a clay mineral known as serpentine, bombarded it, and examined the changes in the spectral properties to see if the changes in any way to be more similar to the C-type asteroids. Next slide, please. They used two approaches. With method 1, they first impacted multiple samples once and analyzed the different areas on the impact sites. With method 2, the second approach, they impacted one sample site multiple times and analyzed the same area after each successive impact. Next slide, please. This graph is based on the reflectance data. We have an example on region D, which is the area of the spectra highlighted in blue. Next slide, please. We zoomed in on this area and fit a line to the shoulders of the spectra for our process called standardization. Next slide, please. I applied standardization by dividing the points on the spectra by the line. Then I applied the polynomial regression and fit a Taylor polynomial to the spectrum to help me take the band area. Shown here is information we learned about this region. And at the bottom is the part of Python code I wrote to do this in every area location combination tested. Next slide, please. I superimposed a couple of spectra to show that there is a band on the very right and left of the spectra that is almost a straight line. I used the best fit line as shown by the black and dark green lines to find the UV VIS and NIR slopes respectively. Next slide, please. Now that we know how I calculated these values, let's take a look at some trends I found with method 1's data in sample 6540 region D combination. Because band area versus location and band depth versus location show similar trends and almost form a linear line when plotted together on the left, it shows that band area and depth are consistent with one another, as expected. Across the different locations, lots of variation of band area and depth show that shocks change the spectra of the material, which was also what we expected. Location topside far, which is the top part of the soil, so it makes sense that it's the most shocked, as indicated by the smaller band area. Location lower side is underneath the top layer, so it also makes sense that it is less shocked, as indicated by the slightly higher band area. Location top unshocked is named unshocked because they thought the location was unshocked. However, since the band area is still low there, it actually shows that it has been shocked. Next slide, please. For the same sample region combination, I graphed the UV VIS versus NIR slope. We do see changes in the slope, so we know that weathering is going on, but the correlation is not as clearly defined. We're still trying to analyze and interpret the meaning of this graph and trying to figure out if it is what we expected and what it says about the amount of weathering. Next slide, please. Now let's move on to another example, this time for analyzing with method 2 data. What they call control, which is on the most left, has 0 impact, and each successive impact is the next one over. We definitely see some shock going on with the reduction in band area for the second and third impacts. However, one impact doesn't shock a lot of material, so if you recombine it, the odds are that there might not be any shocked material in the next sample. Next slide, please. Band depth doesn't change a lot. For the middle two, band area changed, but band depth doesn't change as much. Next slide, please. Band minimum using both the polynomial fit on the left and the actual data points on the right didn't change much either, which was expected. For UV-VIS and NIR, next slide, please. For UV-VIS and NIR slopes respectively, sorry about that. For UV-VIS and NIR slopes respectively, for UV-VIS slopes, sorry about that. So for UV-VIS and NIR slopes, we expected the middle two in each group to be different from the rest, but they are not, which is really baffling. Next slide, please. What we found from analyzing our data with the mineral serpentine was that micrometeorite bombardment produces shock effects. These shock effects change the band area and the band depth, and they also affected the spectral slope a little. Next slide, please. Next steps. Right now, we've only been looking at one mineral, serpentine, that is common in carbonation chondrite meteorites. The next few experiments will involve simulated regolith material from C-type and S-type asteroids. We use simulated materials because actual samples are in small quantities and are very rare, so we want to avoid doing unnecessary destructive experiments with them. And then we'll do radiation and impact experiments on both simulant types, on C-type and S-type asteroids in the fall. Next slide, please. And here is the second project, about lunar swirls on the moon. Next slide, please. Our second project, which we are yet to finish and will continue doing in the fall, is about understanding a fascinating feature on the moon's surface called lunar swirls. The lunar swirls are places on the moon that have magnetic anomalies and show swirling patterns of bright and dark soil. We actually call the soil on the moon regolith because usually the word soil means that it has gone through biological decomposition processes, which the regolith on the moon didn't go through. There are two possible processes. First, the magnetic field near these lunar swirls can shield it from the solar wind, decreasing the space weathering of bright areas. Second, the magnetic field can also trap dust. Dust is the smallest particle of the soil, and they are also the brightest part of the lunar soil. These small dust particles can be charged by the solar wind, so that when they encounter a magnetic field, they get trapped. Our question is, which process is making the lunar swirl? The structure of the regolith, i.e. the grain size, porosity, compaction, roughness, would be different by the two processes. So by analyzing the structure of the regolith, we could figure out which of the two processes was creating the lunar swirls. Next slide, please. This is the region we are currently studying. It is called Muscovine. Next slide, please. This is a snippet of the code I wrote to study this region. Next slide, please. We are in the process of running our models that use the reflectance data of the surface to understand the regolith structure, so we'll have to analyze the results later. And after we've got the results from Muscovine, another area in Reiner Gamma is the region we are going to be studying next in the fall. Next slide, please. Although we are not finished yet, I'd like to take this opportunity to give a special thanks to Dr. Deborah Domingue, Dr. Kominsky, Dr. Rico, NASA, and everyone else in the program for making this opportunity possible. I really couldn't have done it without the guidance and support from all of you. And this wraps up my presentation for today. Thank you all so much for listening. I hope you all enjoyed it and have a wonderful rest of your day.